LMC also contains notable supernova remnants, including SN 1987A, the closest observed supernova in modern history. SN 1987A presented an unprecedented opportunity to study the life cycle of massive stars and how supernova shock waves interact with their surroundings. The Magellanic Galaxy is composed of both young and old stellar populations, making it a crucial subject for studying galaxy evolution over cosmic timescales. It hosts numerous globular clusters, open clusters, and variable stars, including RR Lyrae and Cepheid variables. These stars play a vital role in calibrating the cosmic distance scale, as their predictable luminosity variations serve as standard candles. This calibration is essential for determining the Hubble constant and refining our understanding of the universe's expansion rate. Research into the structure of the Magellanic system reveals its dynamic interactions with the Milky Way and its smaller companion, the Small Magellanic Cloud, SMC. These gravitational interactions cause tidal distortion of gas and stars, Magellan structure extending from both galaxies. These processes likely contribute to the irregular morphology of this satellite galaxy and stimulate its star formation activity. The composition and metallicity of the Magellanic satellite present another area of scientific interest. With a lower metallicity than the Milky Way, it serves as a valuable proxy for studying the conditions of early galaxies in the universe. Its interstellar medium is rich in neutral hydrogen and molecular gas, both fundamental to star formation. Observing its chemical abundances and dust content helps astronomers model the chemical enrichment of galaxies and understand how feedback mechanisms influence their evolution. The Magellanic neighbor is also central to studies of dark matter distribution in galaxies. Since its mass is largely dominated by dark matter, it provides an opportunity to investigate the properties and behavior of this elusive substance. By analyzing its rotation curve, gravitational lensing effects, and tidal interactions, astronomers gain deeper insights into the nature and large-scale distribution of dark matter. Observations from advanced telescopes, including the Hubble Space Telescope, the Atacama Large Millimeter/Submillimeter Array, ALMA, and ground-based observatories, have significantly expanded our understanding of this nearby galaxy. Future missions, such as those planned with the James Webb Space Telescope, JWST, promise to uncover even more details. Multi-wavelength studies, from X-rays to radio waves, continue to reveal the complexities of its structure, active star-specific importance, the Magellanic prominent place in cultural astronomy. Of the Southern Hemisphere have long incorporated it into their mythologies and cosmologies, often viewing it as a celestial companion to the Milky Way or a distinct cosmic entity. Its visibility to the naked eye makes it a familiar and awe-inspiring feature of the southern night sky, inspiring wonder for millennia. As a cornerstone of astrophysical research, the Magellanic Companion bridges our understanding of local galactic processes with the broader context of cosmic evolution. By studying this neighboring galaxy, scientists uncover fundamental mechanisms shaping galaxies and their components, providing a window into the history and future of cosmic structures. The Magellanic stellar system also has a fascinating star formation history. Spectroscopic and photometric studies reveal that it has experienced multiple bursts of star formation over time. These believed to be closely interacting the SMC and the Milky Way. Gravitational forces from these interaction compressions in medium, leading to intense formation. the opportunity to study how galactic interactions shape their evolutionary trajectories. The rotation curve of the Magellanic Disk is another key area of investigation, shedding light on its mass distribution. By measuring the velocities of stars and gas within the galaxy, astronomers infer the presence of dark matter. Observations suggest that, like most galaxies, it possesses a substantial dark matter halo extending far beyond its visible disk. Understanding the characteristics of this halo is crucial for unraveling the nature of dark matter, one of the greatest mysteries in modern astrophysics. One of the most intriguing aspects of the Magellanic Cluster is its ability to host a diverse array of stellar remnants, including white dwarfs, neutron stars, and black holes. Its dense star clusters provide ideal environments for the formation of such remnants, which offer valuable insights into the final stages of stellar evolution. Observations of X-ray binaries provide on the compact objects and their stellar shedding light on the physics of accretion and relativity. Additionally, the Magellanic globes are invaluable for studying the early stages of formation. These ancient structures, among the oldest in the universe, contain stars with extremely low metallicities, providing insight into the conditions that prevailed during the universe's infancy. The distribution and age of these clusters also offer clues about the Magellanic satellite's past interactions with other galaxies, helping to reconstruct its orbital history. In the context of stellar evolution, the Magellanic system serves as a natural laboratory for understanding how stars of different masses evolve and reach their final stages. The presence of massive stars, including Wolf-Rayet stars and red supergiants, allows researchers to investigate the leading to supernova explosions and the formation of compact remnants like neutron stars. The Tarantula Nebula, in particular, remains a focal point as it hosts some of the most massive stars ever observed, exceeding 100 solar. The Magellanic Galaxy also plays a significant role in our understanding of the cosmic baryon cycle. Observations of its gaseous halo and the Magellanic Stream, a vast ribbon of gas at the LMC and SMC, provide crucial data on how galaxies acquire, retain, and lose gas over time. This process is essential for regulating star formation and shaping galactic evolution. The Magellanic Stream, composed primarily of nitrogen, is believed to have been stripped from these galaxies during past interactions, serving as a potential reservoir of material that may eventually accrete onto the Milky Way. Moreover, the Magellanic Companion provides a unique opportunity to study the interaction between magnetic fields and the interstellar medium. The alignment of dust grains and the polarization of starlight observed within the LMC reveal large-scale magnetic fields that influence gas dynamics and molecular cloud formation. Understanding these processes is crucial for developing comprehensive models of galaxy evolution. The future of research on the Magellanic Nebula holds immense promise with the advent of next-generation observatories. Instruments like the James Webb Space JWST will enable to study its stars in unprecedented stages of star and planet formation. Meanwhile, radio telescopes such as the Square Kilometre Array (SKA) will map its neutral hydrogen distribution with ocean, providing new insights into its gas dynamics and interaction history. Ground-based facilities like the Extremely Large Telescope (ELT) will further contribute by resolving individual stars within this galaxy, allowing for precise measurements of their chemical compositions and ages. As our knowledge of the Magellanic Cluster deepens, it becomes increasingly clear that this nearby galaxy is answering some of the most profound questions in astrophysics. From the nature of dark matter to the mechanisms driving star formation and galaxy interactions, the LMC continues to yield crucial insights into the workings of the universe. The Magellanic Cloud is also an invaluable resource for studying chemical enrichment in galaxies. Its unique metallicity gradient, which varies with distance from its center, offers a window heavy elements are synthesized and distributed over time. By analyzing the abundance patterns of elements like oxygen, carbon, and iron across different regions, researchers can reconstruct its history and supernova activity. These studies are particularly significant for understanding the origins of life-essential elements, such as carbon and oxygen, which dying stars release into the interstellar medium. Another key area of investigation is the LMC's role in galaxy mergers. As it continues interacting with the Milky Way, it gradually loses mass through tidal stripping. This process not only alters the Magellanic satellite structure but also contributes to the formation of stellar streams and the accretion of gas onto the Milky Way. In several billion years, the LMC is predicted to merge with our galaxy, an event that will have profound effects on the Milky Way's structure and dynamics. Studying these interactions offers a unique opportunity to model the physics of galaxy mergers, a fundamental process in the hierarchical galaxies throughout the universe. Furthermore, the Magellanic Neighbor's position within the local group allows astronomers to investigate how its radiation field impacts the interstellar medium. Intense ultraviolet radiation from young, massive stars in regions like the Tarantula Nebula drives powerful stellar winds surrounding, creating intricate structures such as bubbles, shells, and filaments. These features are crucial for understanding feedback in galaxies, where energy and momentum from stars regulate star formation by either compressing or dipolar clouds. One of the Magellanic System's most significant contributions to astrophysics lies in its population of variable stars. Classical Cepheids, for instance, are abundant and have played a crucial role in refining the cosmic distance scale. Their well-established relationship between luminosity and pulsation period provides an accurate method for measuring extragalactic distances, ultimately helping to determine the Hubble constant. Observations of these stars have enabled astronomers to achieve some of the most precise measurements of cosmic, significantly reducing uncertainties in our understanding of growth rate. This neighboring galaxy also serves as a key benchmark for studying the interaction between dark matter and baryonic matter in low-mass galaxies. Simulations of its evolution within the Milky Way's gravitational field suggest that its dark matter halo may be asymmetric, shaped by tidal forces and past interactions. By comparing observational data with theoretical, researchers continue to refine their understanding of dark matter's influence on galactic dynamics and structure formation. Additionally, the Magellanic Nebula provides an exceptional laboratory for studying supernova remnants, SNRs. The diversity of these remnants, including those from nuclear supernovae, offers a comprehensive view of how these explosive events impact their surroundings. Multi-wavelength observations spanning X-ray, optical, and radio frequencies reveal details about explosion mechanisms, ejected material, and the influence of supernova shocks on interstellar gas. Its rich population of planetary nebulae and asymptotic giant branch, AGB, stars provides crucial data on the late stages of stellar evolution. By studying how stars shed their outer layers, astronomers gain insight into the enrichment of the interstellar medium with heavy elements. Observations of dust production in AGB stars further enhance our understanding of dust formation and recycling in galaxies, processes that influence formation and the cooling of interstellar gas. A focal point in stellar evolution research, this galaxy provides an ideal environment for studying stars across a wide range of ages. Its well-resolved stellar populations offer key insights into how galaxies evolve over time. The presence of ancient stars acts as a fossil record of the Earth, allowing astronomers to reconstruct its chemical and dynamical history. Differences in metallicity in the central bar and outer regions further highlight the complexities of galactic evolution. The gravitational interplay between this system and its smaller companion, the small Magellanic Cloud, remains a cornerstone of modern astrophysics. Their long-term interaction has given rise to structures such as the Magellanic Bridge, a stream of stars and gas linking both galaxies, and the Magellanic Stream, a massive tail of gas trailing behind them. These formations provide an excellent laboratory for understanding tidal interaction dynamics, and the stripping processes that shape cosmic timescales. Its most active region, Tarantula Nebula, stands out as a key site for studying the formation of massive stars. Hosting an exceptionally dense population of young stars and clusters, it is often compared to the intense star-forming environments of the early universe. Observing this nebula allows astronomers to explore the conditions under which the first generations of stars formed and how their energetic feedback influenced surroundings. Within the nebula are 136 massive stars ever discovered, challenging existing theories of stellar evolution. Beyond its stellar population, this satellite of the Milky Way is a valuable resource for understanding the complex relationship between and dust in galaxies. Its interstellar medium, rich in neutral hydrogen, molecular clouds, and ionized regions, is studied extensively across multiple wavelengths. These observations reveal intricate feedback mechanisms, where energy from stars regulates the cycling of gas and dust, shaping future star formation. The Magellanic System is pivotal in studying cosmic reionization, the epoch when the first galaxies ionized the universe's pervasive neutral hydrogen. Its low metallicity and active star formation make it a valuable proxy for early galactic conditions. By analyzing the ultraviolet radiation escaping from its star-forming regions, researchers gained how the first galaxies contributed to reionismos. Advances in spectroscopy allow astronomers to map its chemical enrichment history with increasing precision. Detailed measurements of elements like magnesium, silicon, and iron provide a timeline of nucleosynthesis events. These studies reveal multiple star-forming episodes punctuated by quiescent periods of renewed activity driven by external interactions. The chemical signatures of ancient stars also hint at the influence of different supernova types, including core collapse and type Ia explosions. The Magellanic Companion is further notable for its role in gravitational microlensing. As one of the Milky Way's closest neighbors, it frequently aligns with background stars, creating opportunities to observe these rare phenomena. Microlensing events have been used to search for dark matter in the form of machos, massive compact halo objects, and to characterize exoplanets within the system. Findings from these studies have placed important constraints on dark matter's nature while expanding our knowledge of planetary systems in nearby galaxies. Additionally, this galactic neighbor plays a crucial role in understanding the dynamics of galaxy groups. Alongside the Small Magellanic Cloud, SMC, and the Milky Way, it forms a hierarchical system that exemplifies how galaxies evolve in a gravitationally bound environment. Interactions refine simulations of galaxy group dynamics, helping to interpret the large-scale structure of the universe. Beyond structural and stellar features, the Magellanic Cloud serves as a laboratory for investigating the life cycle of interstellar matter and the cosmic processes shaping galactic ecosystems. Its network of supernova remnants, SNRs, illuminates the v of massive stars while influencing their host galaxy. The relatively low extinction and minimal foreground interference make it an ideal target for multi-wavelength studies of these remnants. One of the most significant events, SN 1987A, provided an unprecedented real-time view of a supernova's evolution, from its initial outburst to the expanding debris field. The wealth of data from this explosion has driven decades of theoretical research into stellar death, neutron star formation, creation. Another critical area of study is the search for stellar streams, elongated structures of stars and gas formed through tidal interactions. The Magellanic Stream, a massive gaseous tail stretching hundreds of thousands of light-years, stands as one of the most prominent examples. Composed mainly of hydrogen, it represents material stripped from both the LMC and SMC through gravitational encounters with each other and the Milky Way. Understanding its structure and motion provides valuable insight into the Milky Way's gravitational potential and dark matter distribution. High-resolution maps from radio telescopes such as Meerkat and ESCAP have revealed intricate substructures, shedding light on the complex forces shaping the stream. Magellanic Galaxy's star-forming regions, particularly the Tarantula Nebula, offer unparalleled opportunities to study the birth of massive stars. While this nebula is the most extreme example, smaller regions throughout the galaxy provide additional insight into how different environments affect star formation. Variations in metallicity across the system allow astronomers to explore how element abundance influences collapse, protostar formation, and stellar feedback. These findings have broad implications for understanding the early universe, where low metallicity was the norm. In the realm of cosmic distances, this system remains a cornerstone. Its vast population of classical Cepheid variable stars has long been instrumental in refining the cosmic distance scale. The well-calibrated luminosity-period relationship of these stars provides a fundamental rung on the cosmic distance ladder. Recent observations with the Hubble Space Telescope and Gaia have further improved this calibration, solidifying its role as a key benchmark for measuring the Hubble constant. However, ongoing discrepancies between different methods, known as the Hubble tension, persist, keeping the LMC at the forefront of efforts to resolve this cosmic puzzle. Success neighbors, the Large Cloud continues to captivate astronomers, offering a window into stellar evolution, galaxy interaction, and cosmology. Its proximity to the Milky Way enables detailed observations that would be impossible for more distant galaxies, making it an invaluable testbed for studying fundamental astrophysical processes. Scale, the LMC's eventual merger with the Milky Way presents a fascinating future for both galaxies. Simulations predict that this event, expected in about 2.5 billion years, will significantly reshape the Milky Way. Substantial mass, estimated at around 10% of our galaxies, the encounter could reorganize the Milky Way's disk of star formation and create ripples in the stellar halo. This process will also redistribute dark matter, providing a natural experiment in galaxy assembly dynamics. The LMC's magnetic field adds another dimension to its complexity. Observations using polarized light reveal large-scale magnetic structures permeating the galaxy, influencing gas flows, molecular cloud formation, and cosmic ray propagation. Investigating these fields will insight origins and evolution, a topic still not fully understood in astrophysics. professional research. LMC is a source of inspiration for astronomers and photographers. Visible to the naked eye from the southern hemisphere, it has long been a cultural landmark, a pure mythology, and aiding navigation. Through telescopes, star clusters and nebulae showcase dynamic cosmic processes, connecting observers to the broader universe. From individual stars to intergalactic interactions, this galaxy remains central to astrophysical research. It bridges the local and the universal, offering a unique glimpse into the forces shaping the cosmos. Its relative proximity allows astronomers to examine processes that are otherwise challenging to observe in more distant systems. As one of the Milky Way's closest satellites, the LMC provides a window into the nature of galaxies while contributing to broader cosmological studies. Complexity spans diverse components, stellar populations, interstellar medium, dynamic and fundamental physics. Interstellar LMC plays a crucial role in the galaxy's life cycle. Dust grains, atmospheres of aging stars and supernovae, absorb and scatter light, re-emitting it in the infrared. Observations from the Spitzer Space Telescope and Herschel Space Observatory show notable differences in dust composition compared to the Milky Way, likely due to its lower metallicity. These variations affect star formation, as dust aids in cooling molecular clouds to temperatures suitable for stellar birth. The galaxy hosts a remarkable concentration of massive stars and stellar clusters. Several regions experience intense starburst activity, with conditions similar to those in the early universe. The Tarantula Nebula, for instance, contains thousands of massive stars, including some of the most luminous ever recorded. Their powerful stellar winds and short lifespans influence surrounding gas, enriching it with heavy elements through supernova explosions. These processes drive chemical evolution and regulate star formation. Beyond stellar evolution, the LMC plays an important role in gravitational wave research. Its numerous binary systems may include progenitors of neutron star or black hole mergers, events that produce detectable gravitational waves. Observatories like LIGO and Virgo rely on these mergers to study extreme gravity and dense matter physics. Examining compact binary systems in this galaxy helps refine models of their formation and eventual coalescence, shedding light on the origins of gravitational wave signals. Another key area of study involves its gravitational influence on the Milky Way's dark matter halo. The LMC's substantial mass disturbs the surrounding stellar halo, leaving observable imprints of stars. Data from the Gaia Space Telescope, which provides high-precision measurements of stellar positions and motions, have been instrumental in disturbances. Modeling the interactions between the LMC and Milky Way is offering new insights into the shape, mass, and behavior of dark matter. The LMC also serves as a natural testbed for understanding galaxy formation. As a low-mass system, clues about conditions in the early universe when small galaxies merged to form larger structures. Simulations of its evolution, combined with observations of its structure and composition, provide a framework for studying how galaxies grow over cosmic time. Its interactions with the SMC and Milky Way add another layer of complexity, highlighting how gravitational forces and environmental factors shape galactic evolution. Studies of its star formation history, based on photometric and spectroscopic surveys, reveal a pattern of episodic activity. Periods of intense star formation alternate with quieter phases, likely triggered by interactions with the Milky Way and SMC. These gravitational encounters compress gas reservoirs, inducing new star formation while simultaneously stripping material, contributing to structures like the Magellanic Stream. This cyclicalness provides crucial data for understanding how galaxies evolve over billions of years. Ongoing and future missions will further expand our knowledge of this galaxy. Observations with the James Webb Space Telescope, JWST, are expected to reveal new details about its star-forming regions, while radio arrays like ESCAP and Meerkat continue mapping the Magellanic Stream in unprecedented detail. Ground-based facilities, including the extremely ELT, will enhance studies of individual stars and chemical compositions. By continuing to study the LMC, astronomers are uncovering fundamental insights into dark matter, stellar evolution, and galaxy interactions. Whether as a nearby laboratory for astrophysical phenomena or a glimpse into the distant past, this remarkable satellite remains essential for understanding the universe's history. The LMC's status as an intermediate mass galaxy with low metallicity makes it a crucial laboratory for studying planetation and evolution. Lower metallicities are thought to influence planet formation, particularly for terrestrial planets, by limiting the availability of heavy elements essential for their development. Detecting exoplanets in the LMC is challenging due to its distance, but ongoing and future missions, such as the Nancy Grace Roman Space Telescope, may enable their discovery through microlensing events, providing valuable insights into planetary formation under such conditions. Another intriguing area of study is the LMC's magnetic field, revealed through polarimetric observations. Magnetic fields play a fundamental role in shaping galaxies by influencing gas flows, star formation, and cosmic ray propagation. While weaker than the Milky Way's, the LMC's field exhibits features that trace spiral and tidal features. Investigating these magnetic properties could enhance our understanding of their origins and evolution across different galactic environments. With upcoming observatories set to expand our knowledge, the future of LMC research is promising. The James Webb Space Telescope, JWST, will provide an unprecedented view of star formation regions, probing their structure and chemistry in detail. Meanwhile, the Square Kilometre Array, SKA, will map neutral hydrogen distribution, revealing gas dynamics and interactions. These efforts will complement data from Gaia, which continues to refine our understanding of stellar populations and kinematics in the LMC. The LMC remains central to astrophysics, offering an environment for studying galaxy evolution, stars, and cosmic processes. Its history and unique properties provide a natural laboratory for exploring a broad range of phenomena, making it one of the most extensively examined extragalactic objects. Among the most compelling topics is its role in cosmic gas dynamics. The LMC contains vast reservoirs of neutral hydrogen, molecular gas, and ionized regions, essential for fueling star formation. Observations with ATCA and ALMA have revealed intricate interstellar structures, including filaments, shells, and expanding bubbles, often linked to feedback from young stars and supernovae. Studying these features helps astronomers understand and momentum stars regulate the formation of future generations. The LMC also provides key insights into galactic chemical evolution. Relatively low metals conditions in the early universe, offering a glimpse into the processes that shaped the first galaxies. Spectroscopic studies have mapped the abundance patterns of heavy elements produced and sterilized in AGB stars, refining models of nucleosynthesis and interstellar medium enrichment. Another fascinating LMC's population of pulsars and compact stellar supernova as prime locations for neutron star and black hole discoveries. Pulsars, rapidly rotating neutron stars, act as precise cosmic clocks, helping probe interstellar medium properties, test general relativity, and study extreme matter physics. Binary pulsars within the LMC offer unique opportunities to explore accretion dynamics and gravitational interactions. The galaxy's extended stellar halo provides further clues about its formation history. Observations suggest that this diffuse structure contains relics and accretion events, preserving a record of interactions with smaller companions and the Milky Way. Analyzing the motions and compositions of halo stars enables astronomers to reconstruct the LMC's evolutionary timeline and gain insights into hierarchical galaxy assembly. In addition, the LMC's central bar and spiral-like features are key areas of interest. These structures likely result from internal dynamics and gravitational interactions with the Small Magellanic Cloud, SMC, and Milky Way. The central bar appears to host younger stellar populations compared to the outer regions, underscoring the complex relationship between galactic dynamics and star formation. High-resolution simulations, combined with observational data, are helping to unravel the processes that shape these features. As a satellite of the Milky Way, the LMC is also a crucial testbed for studying dark matter. Its surrounding dark matter halo influences its rotation curve, tidal interactions, and overall stability. Comparing observational data with theoretical models allows researchers to constrain dark matter distribution and density, shedding light on this elusive component of the universe. The LMC's ongoing interaction with the Milky Way provides further opportunities to probe dark matter by studying gravitational perturbations and their effects on stellar motion. The LMC's variable stars have played a vital role in calibrating cosmic distances. Alongside Cepheid variables, it contains a large population of RR Lyrae stars, excellent standard candles for measuring extragalactic distances. These older, lower-mass pulsators provide complementary data for refining the cosmic distance ladder. Accurate measurements of the LMC's distance are essential for reducing uncertainties in key cosmologies, including the Hubble constant and the universe's age. As part of an ongoing gravitational interaction with the SMC and Milky Way, the LMC is actively shaping and being shaped by its surroundings. These interactions have produced spectacular structures such as the Magellanic Bridge, a stellar and gaseous link between the LMC and SMC, and the Magellanic Stream, an enormous gas trail extending across the southern sky. These features provide direct evidence of tidal forces at work, serving as a laboratory for studying material exchange between galaxies. Understanding these processes is fundamental to modeling the hierarchical growth of galactic systems in the broader context of cosmic evolution. The future of research on the Large Magellanic Cloud, LMC, is set to be transformative with the next generation of astronomical observatories. The Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, will map the galaxy in unprecedented detail, uncovering faint structures and transient phenomena previously beyond detection. The James Webb Space Telescope, JWST, will probe deep into its star-forming regions, revealing the birthplaces of stars and planets, while radio facilities like the Square Kilometre Array will provide unparalleled to its gas dynamics, interactions with the Milky Way role in the cosmic baryon cycle, history of stars, gas, and dynamic interaction. LMC continues to be a cornerstone in our understanding of galactic evolution. The study of its unique characteristics not only advances our knowledge of galaxy formation but also connects us to the broader history of cosmic development. Its proximity, combined with its distinct composition and history, makes it a natural laboratory for studying phenomena ranging from local stellar to large-scale cosmic interactions. One particularly exciting avenue of research is its role in the creation and recycling of heavy elements. Active stars such as the Tarantula Nebula act as cosmic furnaces where reactions forge elements heavier than hydrogen and helium. These elements are subsequently dispersed into the interstellar medium through stellar winds and supernova explosions, enriching surrounding gas and fueling the formation of new stars and planets. Observing these processes in the LMC helps refine models of galactic chemical evolution, on how the universe evolved from a state into the complex galaxies we see. The LMC also serves as an important testbed for studying the life cycle of star clusters. Unlike the Milky Way, where dense dust obscures many clusters, its low foreground extinction allows for clear observations of stellar groupings at various evolutionary stages. This includes massive young clusters like R136, as well as older globular clusters that serve as a fossil record of past galactic activity. These observations help answer fundamental questions about how clusters form, evolve, and as well as their influence on galactic structure. Another intriguing feature is its population of planetary nebulae, expanding shells of gas ejected by dying stars. These objects offer valuable insights into the late stages of stellar evolution, particularly for low and intermediate mass stars. By studying the shapes and dynamics of planetary nebulae, astronomers gain a better understanding of how stars enrich their surroundings with elements like carbon and nitrogen. Additionally, the LMC's relatively low opportunity to explore how a galaxy's chemical composition influences the behavior of planetary nebulae. The galaxy's rich collection of binaries and compact objects presents another avenue of profound interest. X-ray binaries, in which a neutron star or black hole accretes material from a companion, serve as natural laboratories for testing theories of accretion and relativistic jet formation. The recent detection of gravitational waves from black hole mergers has heightened interest in the LMC as a possible host for progenitor systems. By studying binary interactions within the galaxy, astronomers refine models of stellar evolution and compact object mergers, enhancing of gravitational wave events. On a larger scale, the LMC is crucial for understanding the assembly of the local groups, the Milky Way, Andromeda, and galaxies. Simulations suggest it may have been more massive in the past, potentially losing a portion of its material through interactions with the Milky Way. These findings have profound implications for our understanding of satellite galaxy evolution and the role of tidal forces in shaping galactic systems. One of its most visually striking features, the Magellanic Stream, remains an area of intense study. This massive trail of gas, stripped from the LMC in Small Magellanic Cloud, SMC, extends across a significant portion of the southern sky. It provides a remarkable opportunity to investigate tidal stripping, ram pressure, and material exchange between galaxies. Recent observations have detected not only hydrogen but also heavier elements, likely ejected through stellar feedback. Understanding the composition and motion of this stream is key to reconstructing past interactions between the LMC, SMC, and the Milky Way. The LMC's ongoing interaction with the Milky Way also offers critical insights into galaxy mergers. As it orbits our galaxy, its gravitational influence distorts the Milky Way's stellar halo, creating ripples and streams that can be traced using Gaia data. These interactions are not only reshaping the LMC itself but also influencing the structure of the Milky Way. Simulations predict that their eventual merger will trigger a significant reorganization of the Milky Way's disk and halo, possibly igniting a burst of star formation. The LMC also plays a role in studying cosmic reionization, the era when the first galaxies ionized the intergalactic medium. The active star-forming regions and low metallicity make it an ideal analog for early universe conditions. By examining how ultraviolet radiation escapes from its regions, astronomers gain insights into how the first galaxies contributed to reionizing the cosmos. These investigations, supported by observations from the Hubble Space Telescope and upcoming data from JWST, gap between the distant past and the present. From the physics of stars to intergalactic interactions, the LMC continues to be an invaluable astrophysical resource. Its role as a benchmark for studying the cosmic baryon cycle, the continuous exchange of gas between galaxies and their surroundings, adds another dimension to its importance. Observations suggest it both from the Magellanic stream and loses gas through stellar feedback and tidal stripping. These are fundamental to sustaining star for billions of years and enriching the intergalactic medium with stellar feedback processes in the LMC further highlight its significance. The Tarantula Nebula, the most active star-forming region in the local group, provides a vivid example of how massive stars shape their environment. Stellar winds, radiation pressure, and supernova explosions create large-scale structures such as bubbles and filaments, regulating gas flow and influencing future motion. Studying these mechanisms refines theoretical models of galaxy evolution by showing how feedback influences gas retention and environment for studying the full life cycle of stars. It hosts numerous protostars at various stages of development, offering a rare opportunity to observe stellar formation in detail. At the other end of the spectrum, its supernova remnants, neutron stars, and black holes provide insights into the most extreme astrophysics, from element synthesis to relativistic jet formation. Variable stars, including Cepheids, RR Lyrae stars, and long-period variables, further reinforce the LMC's value in cosmic distance measurements. Observations of Cepheids within the galaxy have helped refine the period-luminosity relationship, which underpins the cosmic distance ladder. These advancements have reduced uncertainties in Hubble constant calculations, though ongoing discrepancies between measurement methods highlight the need for further study. Its interactions with the SMC and Milky Way have also produced complex tidal structures like the Magellanic Bridge and Magellanic Stream, which serve as natural laboratories for studying gas dynamics and galaxy evolution. Meerkat and ESCAP radio telescopes have revealed intricate details of these structures, improving our understanding of material transfer between galaxies. Magnetic fields in the LMC represent another area of growing interest. Polarization studies show a coherent magnetic structure that follows its spiral and tidal features. These fields influence charged particle gas flow and cosmic ray propagation, making their study essential for magnetism's role in galaxy formation. As advances, the LMC will continue to be an essential reference point for astrophysics. With upcoming surveys, space missions, and high-resolution simulation remains at the heart of the fundamental forces, stars, and the cosmos itself. On a cosmological scale, the Large Magellanic Cloud contributes significantly to our understanding of hierarchical galaxy growth. Simulations suggest it may have once belonged to a larger galaxy before being captured by the Milky Way. It provides valuable insights into the processes of galactic assembly and evolution within the framework of large-scale cosmic structures. Its eventual merger with the Milky Way, expected in several billion, is predicted to reshape both galaxies, triggering bursts of star formation and redistributing dark matter within their halos. Another compelling area of study is the potential presence of exoplanets. While detecting planetary systems within this neighboring galaxy is challenging due to its distance, microlensing surveys have identified promise. These discoveries offer a glimpse into planetary formation in different galactic environments, revealing how factors like metallicity influence the process. Future missions, Nancy Grace Roman Space Telescope, expected to enhance our ability to detect and analyze exoplanets in the Milky Way. The Magellanic Galaxy is a laboratory for fundamental physics. Its rich population of pulsars and binary systems serves as a natural testing ground for gravitational theories and the behavior of matter under extreme conditions. Observations of these objects have been used to test Einstein's relativity, study the equation of state for neutron stars, and investigate the formation of compact stellar. The next generation of observatories promises to unlock even more secrets about this galaxy. The Veris Observatory will conduct deep surveys, mapping faint stars, tidal structures, and transient phenomena with unprecedented precision. The James Webb Space Telescope (ST) will reveal of its star-forming regions and interstellar medium at resolutions previously unattainable. Meanwhile, the SKA will provide detailed hydrogen maps, shedding light on the gas dynamics and interactions shaping the galaxy's evolution. The Great Cloud remains a cornerstone of modern astrophysics, bridging the local distant past. Its study advances our understanding of galactic dynamics and the broader history of cosmic evolution. As one of the Milky Way's most prominent satellite galaxies, it plays a vital role in unraveling the complex interactions over billions of years. One feature is its vibrant star-forming regions, most notably the Tarantula Nebula. This colossal nebula, the most active stellar nursery in the local group, produces massive stars at an extraordinary rate. The intense ultraviolet radiation from these young, hot stars ionizes the surrounding gas, shaping intricate structures within the interstellar medium. Energy feedback from massive stars influences star formation across the region and enriches surrounding gas with heavy elements. The Magellanic stellar cloud provides a unique environment for studying stellar evolution across various masses and life stages. Its population of Wolf-Rayet stars, red supergiants, and other massive objects offers valuable insights into how stars evolve and end their lives, whether as supernovae, neutron stars, or black holes. Its lower metallicity further makes it a compelling analog for the conditions of the early universe where similar environments were more common. A critical component of the Magellanic Nebula is its population of variable stars. Classical Cepheids, RR Lyrae stars, and other pulsating objects have played a crucial role in calibrating the cosmic distance scale. These stars function as standard candles, enabling astronomers to refine distance measurements with exceptional accuracy. Pinpointing its exact distance is key to reducing uncertainties in the Hubble constant, further refining our understanding of the universe's expansion. The Magellanic Companion is also a valuable subject for studying interstellar gas dynamics. Its vast neutral hydrogen and molecular clouds build a picture of how gas moves and cycles through a galaxy. Observations have revealed the interplay between internal processes, feedback, and external influences like tidal interactions with the Milky Way and small Magellanic Cloud. These enhance our knowledge of how gas is recycled and redistributed, fueling star formation and galactic evolution. The halo is another focus of intense study. The rotation curve of the Magellanic Galactic Companion suggests it is embedded in a substantial halo of dark matter, whose distribution and density remain curious. Modeling the gravitational effects between this galaxy, the Milky Way, and the SMC provides critical data on dark matter's role in shaping galactic structures. The Magellanic Cosmic Cluster is a real-time view of galaxy interactions. Tidal for this system, the SMC, and the Milky Way have created dramatic structures such as the Magellanic Stream, a massive tail of neutral hydrogen stretching across the southern sky. These features preserve the history of interactions between these galaxies, providing an observational record of material exchange effects. Understanding their formation helps reconstruct the sequence of events that shape the present-day Magellanic dwarf galaxy and similar systems in the universe. With its irregular shape and dynamic history, this satellite remains one of the most valuable objects for studying small galaxies and their role in the cosmic ecosystem. Its position in the local group, coupled with active star formation and interactions with larger galaxies, makes it a prime laboratory for understanding the life cycles of galaxies and stars. Observations of this evolving system will continue to refine our knowledge of galactic mergers, interstellar matter cycles, and fundamental astrophysical. The Magellanic Dwarf Galaxy remains an essential piece of the puzzle in understanding how galaxies grow, interact, and transform across cosmic time. A fascinating feature of this southern stellar companion is its diverse population of star clusters. These include ancient globular clusters, remnants of the galaxy's early history, as well as younger open clusters that capture snapshots of star formation. By analyzing these stellar groupings, astronomers can trace the evolution of this system, uncovering how it has grown through interactions with its cosmic surroundings. Such clusters provide critical clues about the conditions under which stars and planets formed in the early universe, preserving ancient metallicities and dynamical patterns. The Magellanic Star also hosts the most forming region in the local group. This vast stellar nursery contains the R130, home to some of the most massive and luminous stars ever discovered. Intense radiation and stellar winds from these giants sculpt surrounding gas clouds, carving intricate cavities in the interstellar medium. Studying these processes offers a rare opportunity to observe stellar feedback in action, refining models of starburst galaxies across cosmic history. This cosmic companion is also a prime site for exploring galactic gas flows. It contains one of the richest reservoirs of neutral hydrogen in the local group, with radio surveys revealing filaments and tidal shaped by gravitational interactions. Encounters with the small Magellanic Cloud, SMC, and the Milky Way have stripped gas from its outer regions, forming the Magellanic Stream and Bridge. These tidal structures serve as an invaluable laboratory for understanding how galaxies exchange material and how gravitational forces influence their evolution. Another striking aspect of this starburst galaxy is its distinctive stellar population. With lower metallicity than the Milky Way, it provides an analog for conditions in early galaxies, offering insights into stellar nucleosynthesis under primordial conditions. The chemical enrichment of the interstellar medium by supernovae within this system enhances our understanding of how galaxies evolve and seed the cosmos with heavier elements. The satellite system is also a crucial natural laboratory for studying dark matter. Simulations indicate that its dark matter halo extends well beyond the visible galaxy, influencing its motion and interaction. Tracking the movements of stars and gas under gravitational influence evidence of the halo's mass and structure. Furthermore, its eventual merger with the Milky Way real-world insights into how galaxies grow by accreting smaller companions, a process fundamental to cosmic evolution. The Great Southern Nebular Cloud, as it is sometimes poetically called, is home to a wide array of compact objects, including neutron stars and black holes. These remnants of stellar collapse provide an excellent testing ground for extreme physics. Observations of X-ray binaries and pulsars within this galaxy help astrophysicists probe the mechanics of accretion disks, relativistic jets, and star interiors, offering key insights into the fundamental laws of matter and gravity. Additionally, this galactic companion plays a crucial role in the overall dynamics of the local group. Its gravitational interactions with the Milky Way and SMC have significantly influenced the structure of all three galaxies, producing tidal streams, bridges, and extended stellar tails. Mapping these structures with instruments like Gaia and next-generation radio allows astronomers to reconstruct the past orbits of these systems, revealing a complex history of interactions spanning billions of years. Extraordinary galactic system, regardless of the name given to it, continues to provide transformative insights into the processes that shape galaxies, stars, and the wider universe. The intergalactic jewel of the sun, often referred to as the Large Magellanic Cloud, occupies a unique position between dwarf galaxies and larger spirals, making it an essential subject for studying galactic evolution, star formation, and cosmic interactions. This remarkable system holds key information about processes that have shaped galaxies throughout the history of the universe. The Southern Stellar Nursery is widely recognized for its prolific star-forming regions, Particula Nebula. This stellar factory mirrors conditions in the early universe, where galaxies underwent intense star formation. Within this nebula, astronomers study how molecular clouds collapse into stars, how radiation and stellar winds sculpt their environments, and how supernovae recycle material back into the same time. The Sky's Star Forge holds a deep record of ancient history, preserving some of the oldest globular clusters in the local group. Valuable data about the universe as it was billions of years ago. Examining their metallicities and kinematics helps astronomers uncover the mechanisms of early galaxy formation and the role of mergers in assembling today's larger systems. Star Arc further dynamic laboratory for galaxy interactions. Its gravitational interplay with the SMC and Milky Way has led to the creation of striking tidal features such as the Magellanic Stream and Bridge. Formations serve as observational proof of how gas and stars are exchanged between galaxies, fueling new bursts of star formation and reshaping galactic ecosystems. The labyrinth of this neighboring galaxy is especially valuable for examining low metallicity environments. Lacking many of the heavier elements common in the Milky Way, it presents a rare opportunity to observe star formation and evolution under conditions that mimic those in the early universe. The chemistry and dynamics of these stars contribute to refining our models of nucleosynthesis and galactic chemical enrichment. The Southern Star Canyon, as some astronomers affectionately call it, is a treasure trove of compact objects. Its supernova remnants, binary systems, and neutron stars allow researchers to explore the physics of extreme environments. Across multiple wavelengths, X-ray, radio, and optical, provide critical data on gravitational interactions, accretion processes, and relativistic phenomena. The Magellanic cosmic reservoir contains vast supplies of neutral hydrogen gas, fueling future generations of stars. Detailed radio surveys track how this gas flows through the galaxy, condenses into molecular clouds, and eventually ignites star formation. These observations also reveal interactions between its gas reservoirs and the Milky Way's halo, shedding light on the broader galactic ecosystem. As an irregular marvel, this galaxy offers a compelling study of morphology's impact on galactic evolution. Unlike well-structured spirals, its irregular shape reflects a turbulent past shaped by forces and external tidal effects. These distortions offer a natural in how galaxies evolve under the influence of gravitational encounters and stellar feedback. The sky's ancient traveler is a key subject in the study of dark matter. The motions of stars and gas reveal the gravitational effects of its extended dark matter halo, which stretches far beyond its visible boundaries. Modeling these dynamics helps researchers constrain the nature and distribution of dark matter, contributing to one of modern physics' most pressing mysteries. Finally, the southern Singularity remains a dynamic part of the local group, continually interacting with its neighbors. The tidal forces it experiences reshaping its own structure, leaving lasting imprints on the Milky Way's stellar halo. Interactions provide a glimpse into the future of the local group and the eventual fates of its member galaxies. As one of the most thoroughly studied extragalactic systems, this southern gem continues to provide new revelations about galaxy formation, stellar evolution, and the intricate web of cosmic interactions shaping the universe. The southern celestial dynamo, widely recognized as the Large Magellanic Cloud, functions as an engine driving our understanding of galaxy dynamics, star formation, and interstellar interactions. With its irregular yet structured form, this remarkable system offers insight into the cosmos, from molecular cloud collapse to large-scale intergalactic flows. The Magellanic Stellar Forge serves as a hub for stellar production, housing the Tarantula Nebula, an exceptionally active star-forming region. This vast nursery provides a real-time model of how massive molecular clouds collapse to form clusters, with stellar feedback, winds and radiation from young, hot stars, sculpting surrounding gas structures. The southern galactic cradle presents stars and ancient relics, making it an ideal site for studying stellar evolution. Ancient globular clusters act as benchmarks for understanding the early universe, while massive young clusters shaping modern galaxies. By analyzing these populations together, astronomers uncover a narrative spanning billions of years. The intergalactic alchemy engine reflects the role of this galaxy in chemical evolution. Its lower metallicity mirrors conditions in the early universe, allowing researchers to study the production and dispersal of elements heavier than helium, such as carbon, oxygen, and iron. Supernovae within this system serve as cosmic alchemists, enriching the interstellar medium and laying the foundation for future stellar and planetary formation. The cosmic tidal sculpture illustrates the profound gravitational interactions it experiences with the Milky Way and small Magellanic Cloud. These forces create vast tidal Magellanic bridge and stream, tracing the exchange of gas between galaxies and shaping their evolution. These features provide a unique laboratory for studying how gravitational forces influence star formation and galactic structure. The sky's hydrogen reservoir highlights the vast stores of neutral hydrogen fueling new generations of stars. Radio observations have mapped intricate voids within this gas, shaped by stellar feedback and gravitational encounters. These findings enhance our understanding of how gas flows sustain stars across cosmic time. The southern cosmic clock reflects the precise and predictable motions of stars and gas. Mapping its rotation curve reveals the presence of an extensive dark matter halo, a hidden framework governs. This provides a valuable testing ground for theories on dark matter's influence in galactic evolution. The Magellanic starburst nexus showcases regions of intense stellar feedback, where supernova explosions and powerful winds inject energy into surrounding gas, creating vast cavities and triggering secondary waves of star formation. These processes role in regulating the galaxy's long-term ability to sustain stellar birth. The celestial collision zone foreshadows an eventual merger with the Milky Way. Over billions of years, it will spiral closer, undergoing tidal disruption and contributing its stars, gas, and dark matter to its larger neighbor. This event mirrors countless mergers that have shaped across the universe, offering a glimpse into the future of galactic evolution. The dynamo of change also serves as a key reference for understanding magnetic fields in galaxies. Polarization studies reveal large-scale magnetism threading through its interstellar medium, influencing and possibly playing a role in star formation. These insights contribute to our broader understanding of magnetism's role in shaping cosmic structures. The Southern Star River represents the ongoing stars and gas between this galaxy, the SMC, and the Milky Way. Stretching across hundreds of thousands of light years, this dynamic feature records past trajectories, detailed by radio and optical surveys. The stellar time observes remnants of past events through its rich populations of variable stars, supernovae, and compact objects like neutron stars and black holes. These stellar fossils provide astronomers with crucial tools for reconstructing its history, tracing cycles of formation, destruction, and renewal. Each perspective, whether as a dark matter laboratory, highlights its importance in unraveling the mysteries of the universe. The Large Magellanic, in all its complexity, stands as one of the most invaluable natural laboratories in astrophysics. It is not just a satellite of the Milky Way but a dynamic system encapsulating the processes that shape galaxies over billions of years. Its significance extends to local group understanding of galactic evolution and the larger-scale structure of the cosmos. At the core of its importance is its ability to link the local and distant universe. By studying its star-forming regions, interstellar medium, and stellar populations, astronomers reconstruct conditions that shaped galaxies in the early epochs of cosmic history. Its low metallicity offers a rare glimpse into environments that parallel the young universe, providing crucial data of how the first galaxies formed, evolved, and enriched their surroundings. Its interactions with the SMC and Milky Way reveal the complexities of galactic motion and material exchange. These gravitational encounters shape the structures of all three galaxies, driving the flow of gas and stars that sustain their evolution. Tidal features like the Magellanic Stream and Bridge serve as records of these forces, offering a direct observational link to processes that take billions of years to unfold. Beyond galaxy evolution, this system paralleled environment for studying the life cycles of stars. From the massive, luminous inhabitants of the Tarantula Nebula to ancient globular clusters and compact remnants, it contains examples of every stage of stellar evolution. Its variable stars, such as Cepheids and RR Lyrae, remain fundamental to refining and scale, anchoring our measurements of the universe's expansion. These contributions are essential in addressing key cosmological questions, including ongoing debates over the Hubble constant. The rich interstellar medium, composed of molecular clouds, neutral hydrogenized gas, supplies the raw material for star formation. Observations reveal how galaxies regulate this process through feedback mechanisms, where energy from massive stars and supernovae shapes the interstellar medium. These interactions are critical to understanding how galaxies sustain star formation over time and how they contribute to the chemical enrichment of intergalactic space. By continuously shaping our understanding of the universe, this southern gem remains at the forefront of astrophysical research, offering endless opportunities to study the mechanisms that govern galaxies, stars, and cosmic evolution. Moreover, this neighboring galaxy plays a crucial role in dark matter research. Its rotational dynamics and tidal interactions with the Milky Way offer direct evidence of dark matter's influence on galaxy evolution. By analyzing its distribution within both the visible structure and halo, researchers gain deeper insights into this elusive substance, which dominates cosmic mass yet remains undetectable through conventional methods. Looking ahead, this dynamic system will remain a cornerstone of astrophysical research for decades. Upcoming observatories promise to reveal even mysteries. Webb Space Telescope will explore its star-forming regions and interstellar dust with unprecedented precision, while the Vera C. Rubin Observatory will map its stellar populations and tidal features in remarkable detail. Additionally, the Square Kilometre Array will refine our understanding of its neutral hydrogen content and its ongoing interactions with the Milky Way. Perhaps one of the most compelling aspects of this galactic neighbor is its future. In approximately 2.5 billion years, it will merge with the Milky Way, triggering transformative events that galaxies. This impending collision provides a real-time example of hierarchical galactic growth, illustrating how stars, gas, and dark matter redistribute over cosmos, processes that have sculpted galaxies. Beyond its scientific importance, this celestial landmark has also held a deep cultural significance. Visible to the naked eye from the southern hemisphere, it has inspired myths, navigational practices, and astronomical observations for millennia. Today, it continues to captivate astronomers as a bridge between our local universe and the vastness beyond. In the end, this satellite galaxy is far more than a companion to the Milky Way. It is a dynamic and evolving system that encapsulates the complexity of the cosmos. From its star clusters and gas flows to its gravitational interactions and dark matter halo, it tells a story of cyclation and continues. It not only expands our knowledge of the universe but also reinforces the of cosmic evolution, an enduring tincture of the cosmos. Black holes are one of the most mysterious and intriguing phenomena in the universe. They are the result of the gravitational collapse of massive stars and are so dense that their gravity prevents even light from escaping from their boundaries. Therefore, they are black and invisible to our eyes, although their presence can be felt through their environmental impact. They occur when a massive star exhausts the fuel needed to sustain nuclear fusion. The star begins to collapse under its own weight, contracting to such a density that a point with an infinite curvature of spacetime called a singularity is formed. The singularity is surrounded by the event horizon, an imaginary boundary beyond which nothing can escape. The event horizon is a kind of threshold that separates the black hole from the outside world. The nature of black holes is studied thanks to Albert Einstein's general theory of relativity. The theory predicts that the mass of the black hole warps spacetime, forming a gravitational well. This deformation is so strong that it affects the trajectories of light and matter. For example, light passing near a black hole can be warped, forming an effect known as gravitational lensing. There are several types of black holes depending on their mass. Stellar black holes are formed by the collapse of massive stars and have a mass that is usually 3 to 10 times the mass of the Sun. Supermassive black holes are found at the centers of galaxies, including our own Milky Way. Their mass reaches millions or even billions of solar masses. Their origin remains a mystery, but they are thought to form due to the merger of smaller black holes and the absorption of matter over billions of years. Another category is intermediate black holes, which have masses ranging from a few hundred to several thousand solar masses. Their presence has only recently been confirmed thanks to modern methods, such as gravitational wave astronomy. The phenomenon of Hawking radiation adds another mystery to the nature of black holes. Stephen Hawking predicted that black holes are not completely black, they can lose mass and energy due to quantum effects, emitting weak thermal radiation. This phenomenon is explained by the interaction of particles and antiparticles at the event horizon. A single particle can fall into a black hole and the other escapes, causing the black hole to gradually evaporate. Space traps are also a place of extreme phenomena. If we imagine that an object falls into a black hole, it undergoes a phenomenon known as spaghettization. This is due to the difference in gravitational forces between the near and far sides of the object. Gravity is so strong that the object stretches into a long and thin thread. The study of black holes is carried out using various methods. For example, telescopes capture the X-ray radiation that is produced when gas and dust are heated to extrude before falling into a black hole. Gravitational waves are also used, fluctuations in spacetime caused by collisions of black holes. In 2015, for the first time, such waves were recorded, which was a revolutionary discovery in physics. These objects can interact with other objects in the universe. For example, they are able to absorb stars that pass too close, forming powerful accretion disks of matter orbiting the event horizon. In such cases, there is an emission of relativistic jets that spread over thousands of light years. However, these cosmic craters are not only destructive. They may also play a key role in galaxy formation. Supermassive dark zones in the centers of galaxies regulate the processes of star formation, influencing the distribution and movement of matter. This relationship between black holes and galaxies is one of the most pressing topics in modern astrophysics. Gravitational collapse objects are also important for studying the fundamental laws of nature. They are laboratories for testing relativity, quantum mechanics, and their interactions. For example, the problem with the information paradox is that quantum mechanics requires the conservation of information, while general relativity assumes its annihilation in a singularity. This question remains unresolved and is one of the key mysteries of physics. The phenomena of space and time capture the imagination of not only scientists, but also a wide audience. They inspire science fiction, where they are often depicted as gateways to other dimensions or time machines. And although these concepts are hypothetical, they stimulate interest in the study of the universe. In 2019, the world saw for the first time a photograph of a black hole taken by the Event Horizon Telescope. This image was a confirmation of the theory of relativity and demonstrated the power of modern technology. Gravitational forces remain one of the most intriguing objects in space. Studying them opens up new horizons for science, helping us better understand the nature of the universe and our place in it. An incredible source of inspiration and research, so it is worth delving even further into aspects of their impact on space, physics, and our understanding of reality. One of the most interesting topics in the study of black holes is their surrounding matter and radiation. When material, such as gas, dust, or even a star, falls into the gravitational field of a black hole, it does not immediately disappear into the singularity. Instead, matter forms an accretion disk, a structure that consists of heated gas orbiting a black hole. Due to friction and gravitational forces, the gas in this disk heats up to millions of degrees, emitting energy in the X-ray spectrum. It is this makes black holes visible to astronomers, because they themselves do not emit light. Supermassive black holes, which are located at the centers of galaxies, are often accompanied by powerful jets of high-energy particles escaping from poles of the accretion disk. These jets can reach thousands of light-years and significantly affect the galaxy's environment. For example, they are able to expel gas, or even stopping the process of star formation. Such interactions are an example of how black holes can influence the evolution of galaxies and the formation of cosmic structures. In addition, they can merge with each other, forming even more massive objects. The merger of these astronomical objects is accompanied by the emission of gravitational waves, which were predicted by Einstein in his general theory of relativity. In 2015, it was possible to register these waves for the first time, and this discovery was revolutionary. It not only confirmed the theory, but also opened a new era in astronomy, the era of gravitational wave observation. Another intriguing topic related to these objects is their formation and growth. Although the process of stellar black hole formation is more or less clear, the origin of supermassive black holes remains a mystery. How did they reach such huge masses in a relatively short time after the Big Bang? There are several theories. One of them suggests that supermassive black holes form from seeds, primordial black holes that appeared in the early universe. Another hypothesis suggests that they grow by absorbing large volumes of matter or merging with other subjects of the astrophysical singularity. Even more exotic is the idea of primordial black holes, which could have arisen shortly after the Big Bang due to fluctuations in the density of matter. Such objects could have a variety of masses, including very small ones. If they exist, primordial black holes could explain some mysterious phenomena, such as the nature of dark matter, which makes up a large part of the mass of the universe but still remains elusive. The existence of these gravitational monsters poses numerous philosophical and theoretical questions to science. For example, is it possible to travel through a black hole? Theorists suggest that a black hole could be a portal to another universe, or even to another time. These ideas remain speculative, but they stimulate scientific research in the field of quantum gravity and the nature of spacetime. The paradox of information in black holes is another unsolved problem in physics. If an object falls into these space traps, all information about its properties seems to be lost when it reaches the singularity. However, quantum mechanics states that information cannot be destroyed. This contradiction has become one of the central questions in modern physics, and solving this puzzle could lead to a revolution in our understanding of quantum mechanics and gravity. Another mystery is the nature of the singularity, which is the central point of a black hole. In a singularity, the laws of physics that we know cease to apply. It is a place of infinite density and curvature of spacetime. Current theories such as quantum gravity and string theory try to explain exactly what happens in a singularity, but there is no definitive answer yet. These light absorbers also have a huge impact on popular culture. They are often depicted in movies, books, and video games as mysterious, dangerous objects, or as means of traveling through time and space. For example, in the movie Interstellar, the gargantua black hole became the centerpiece of the plot, and her image was created using real scientific models, making her one of the most accurate in cinema. In conclusion, black holes are not just mysterious objects that challenge our understanding of the universe. They are the gateway to new knowledge and understanding of how our space works. Studying them is not only a journey into the world of extreme phenomena, but also the key to unraveling the fundamental laws of nature that underlie everything that exists. Black holes remain the focus of attention of astrophysicists and theorists alike, because they open up limitless horizons for scientific research and reflection on the nature of reality. To further understand their essence, it is worth considering additional aspects, such as their connection to dark energy, quantum effects, as well as their role in the large-scale structure of the universe. One of the most exciting theories is the suggestion that black holes may be related to dark energy, a mysterious force that accelerates the expansion of the universe. Some current models put forward the idea that the vacuum energy that surrounds black holes could be a source of dark energy. If this is true, then these gravitational wells play a much larger role in cosmology than we can imagine. It also opens up opportunities for new approaches to solving one of the main mysteries of modern science: why is the universe expanding at an ever faster rate? The quantum aspects of black holes are one of the most active research topics. As mentioned, Stephen Hawking predicted that black holes emit energy through a process known as Hawking radiation. This process demonstrates the interaction of gravity with quantum fields and suggests that black holes can gradually lose mass and eventually evaporate. This phenomenon highlights the relationship between quantum mechanics and general relativity, but also reveals a deep contradiction between the two. These contradictions, known as the information paradox of black holes, stimulated the development of new theories, such as the holographic principle. This principle states that all the information that falls into a black hole is stored on its event horizon in the form of a quantum code. If true, then black holes could act as a kind of storage devices for information about the universe, which opens up exciting prospects for quantum physics. Objects with critical gravity not only destroy, but also create. They play an important role in the formation of galaxies and large-scale structures of the universe. For example, supermassive black holes can act as architects, forming galaxies through their gravitational interaction. Their ability to influence the movement of gas and dust around them creates conditions for star formation. In some cases, however, supermassive black holes can slow down this process if their jets cleanse the galaxy of the gas needed to give birth to stars. One of the most striking phenomena associated with black holes is relativistic jets, or jets. These jets are formed by extreme magnetic fields that are generated by accretion disks around rapidly rotating black holes. Jets contain charged particles that are ejected at speeds close to the speed of light. They are able to penetrate intergalactic space, affecting nearby galaxies and even creating shock waves in intergalactic gas. The study of jets helps scientists better understand not only the nature of black holes, but also the evolution of galaxies and quasars, extremely bright objects that gain energy from the accretion of matter onto supermassive black holes. And while black holes are often associated with destruction, they also open the door to ideas about traveling through space and time. In general relativity, the existence of so-called wormholes is allowed, hypothetical tunnels that can connect different points in spacetime. Although the existence of wormholes has not yet been confirmed, their study offers hope for the development of future interstellar technologies. Gravitational influence zones are ideal objects for testing new theories. They challenge our knowledge of high-energy physics, quantum fields, and gravity. Future research with advanced telescopes such as the Space Telescope James Webb, as well as new gravitational wave detectors, will allow you to penetrate even deeper into their nature. Black holes are not just dark spots on the map of the universe. They are the key to nature's deepest mysteries, from the beginning of time to the limits of space. Studying them not only expands our knowledge of the cosmos, but also raises fundamental questions about what it means to be part of this boundless and mysterious universe. One of the most interesting concepts is the idea that black holes can be energy sources capable of fueling the evolution of galaxies and even creating entire cosmic structures. The enormous amount of energy released during the accretion of matter exceeds the energy produced by stars, and this energy is capable of influencing the chemical composition and dynamics of gas in galaxies. This phenomenon, known as active galactic nucleus feedback, can stop star formation or change the ways in which new galaxies form. Quasars, one of the brightest objects in the universe, are an example of such processes. They are powered by the energy released during the accretion of matter onto supermassive black holes, and their brightness can surpass the glow of all the stars in the galaxy combined. Observations of quasars allow scientists to study the conditions that prevailed in the universe in the early stages of its evolution. Dark matter is another mysterious substance that makes up about 27% of the mass energy of the universe, but does not emit light, so it cannot be observed directly. Black holes are often seen as candidates for the role of reservoirs for dark matter. Although research has not yet provided definitive answers, there are theories that black holes can interact with dark matter particles, creating unique gravitational signatures. For example, if primordial black holes formed in large numbers in the early universe, they could be major components of dark matter. However, this idea remains speculative, since no clear evidence of the existence of such objects has yet been found. Observations of black holes that existed several 100 million years after the Big Bang raise questions about their origins. How were they able to reach such masses in such a short time? One possible answer is the direct collapse hypothesis. In this scenario, large clouds of gas could collapse directly into the black hole, avoiding the star formation stage. Another option is accelerated growth due to the efficient absorption of matter. The study of early black holes allows scientists to better understand the conditions that prevailed in the young universe, including the formation of the first galaxies and stars. Imagine two black holes orbiting each other, gradually getting closer. This process is accompanied by powerful gravitational waves, fluctuations in spacetime that propagate at the speed of light. When two black holes merge, they emit huge amounts of energy in the form of gravitational waves. The first such waves were recorded in 2015 by the LIGO Observatory, which was a revolution in physics. These events not only confirmed the existence of black holes and mergers between them, but also opened up a new way of studying the cosmos. Gravitational waves allow us to hear the universe, allowing us to study objects and phenomena that are inaccessible to conventional telescopes. One of the biggest challenges of modern physics is the unification of two fundamental theories, quantum mechanics and general relativity. Black holes are at the junction of these two sciences, which makes them ideal laboratories for developing new theories such as quantum gravity. For example, the question of whether information that falls into a black hole is stored remains a central problem in physics. If this problem is solved, we can get the key to a theory of everything that will unite all the fundamental interactions of nature. Even though black holes are associated with the end, they can also be the key to the future. There are ideas that the use of energy released during the accretion of matter can provide humanity with an almost infinite source of energy. Such ideas remain fantastic, but they highlight the importance of black holes in understanding not only the cosmos, but also our potential as a species. Compact massive objects continue to capture the imagination and raise questions. Not only are they objects of extreme physical phenomena, but they also make us think about deeper questions of being, such as the nature of reality, time and space. Studying them is a journey that never stops and leads us to discover new facets of the universe. Black holes are objects that never cease to amaze and delight with their mystery. They are the result of an extreme fusion of space and time, where the laws of physics that we know cease to operate in the usual sense. Their appearance requires the fulfillment of strict conditions, but this is what makes them so interesting to explore. A star that has exhausted its nuclear fuel survives a collapse to form an ultradense object with gravity capable of holding even light. This process occurs with the participation of gravity, which begins to prevail over all other forces, causing the matter of the star to contract to extremely small sizes. The result is a singularity, where the density and curvature of space become infinite. An event horizon forms around the singularity, a boundary beyond which even light cannot escape. This makes black holes invisible, but they leave traces in the space around them. Scientists learn about their existence due to the effect on nearby matter or radiation that occurs due to the heating of gas in an accretion disk. The temperature in such disks can reach millions of degrees, generating X-rays that can be recorded with modern telescopes. The study of black holes opens up the opportunity for us to look into the depths of space and time, because they have been formed over billions of years. One of the biggest discoveries in the study of these objects was the observation of gravitational waves caused by the collision of two black holes. These waves not only confirmed the predictions of general relativity, but also made it possible to look at the dynamics of the universe. Black hole mergers are events of colossal proportions in which energy equivalent to several solar masses is released. Some cosmic vortices reach masses that are millions or even billions of times the mass of the Sun. Such objects are called supermassive black holes.